The discussion and the conclusion, like how long and length, because I filled them out, but I'm not sure if they're long enough. But I answered all the questions that were.
If you answer them completely, I would say don't worry about it.
Okay.
And I would say just make sure there's enough detail. I'd say on average, probably the discussion is maybe about a page and the conclusion is like a quarter of a page. The conclusion is usually pretty short.
Okay.
But the discussion can be anywhere between, I'd say half a page and 2 page. I'd say that's kind of the range that I see people having it.
Has anyone turned it in yet?
I don't think so. No, I haven't checked though.
Might be the first one.
Oh, nice.
So you're gonna grade a fun one first.
I probably won't grade them to all of them already.
Really?
Probably.
Man,
I like to.
I already talked it up. I know you want to look at it now.
I do want to look at it, but then it's good. It's good for you don't want to kind of prime yourself from based on one.
Expectations. Yeah.
You want to do it all at once. I want to make sure I'm in the same mood for all of them too.
Yeah.
I don't want to be in a bad mood when I grade yours and then.
Oh, you can't be. I don't think you are a bad one. I write your name down many times.
Oh yeah.
Yeah. The whole reason that the tests were ran in the first place.
Nice.
Yeah. All right, so I think I need to add more to my discussion now. My discussion is like on that much.
Okay. Okay. Yeah, I would just make sure you're answering it just completely and then
And elaborating.
yeah, and elaborating on all the points.
All right, cool. Other than that, we're done.
Thanks.
Hey, could we take a look? Or can we grab our?
Oh, yeah, of course. I'm done with them all, so you guys can take it.
I will be leaving.
Okay.
My cat's medicine, so I'll get up and just leave that way.
Yes, no problem.
Hey.
Okay.
I think I have the same version as here, so I should be able to. So yeah, why don't you do? I will be here tomorrow actually. So normally I'm not, but if you want to come to my office tomorrow at 4 o'clock.
No, I'll come on Thursday.
Okay.
at 9 o'clock.
Okay. Yeah,
Because
no problem.
around 4 is the time I pick up my children.
Yeah, no problem.
And I only have that version on the desktop, so I will try to install it tonight on the laptop.
Okay.
So if you guys on Thursday.
Okay.
Thank you.
Sounds good. Yep. Mhm.
Oh, so right now I'm working on the arm for Rover.
Okay.
And I want to see like, where would I apply the conditions for the arm?
Are you doing it all as one assembly?
So right now we're determining the stress analysis for the person.
Okay, that's perfect. So I would, this is where the cap is.
Yeah.
So I would definitely fix it right here. Right here. So you can do a couple things. And so for the end right here, it makes it pretty straightforward. You can just put the weights of all the components down here. And then just apply that as a base. And then you can also apply center gravity to get the weight of the arm itself. So that'll be applied, and that'll be distributed all through, which is gonna be a lot more interesting. So, yeah, I would start with that. Of course, the stresses and stuff are gonna be on the orient. And so I would do a couple simulations where you apply the force, this way.
Yeah.
And then maybe you rotate the arm upwards, and force, of course, will go down the barrel.
Yeah.
And so I would do a couple simulations with different configurations and see how the stress varies in different rotations.
Okay. And then, because one of the rules, one of the missions for the arm is to pick up around 5 pounds.
Yes.
So how would I Because it's the right now the model is absolutely complete. We just have the first link.
Yeah.
So how would I apply the condition?
Yeah, and so that would be just an additional force or additional weight at the end here. And of course, you only have this model, so if you have additional 5 forces here, that's going to transmit to be another 5 forces here. And so that force basically transmits all the way. So when you're doing the weights of downstream, you just add additional. But again, you can test it out in different configurations. And then once you get the other components catted up, then you can kind of add on those parts of the assembly, and then you just add on the weights and stuff.
It's just the same thing. They just vary.
Yep. Charles, how's it going? Yes, and so the rotational velocity that'll give you basically a centripetal acceleration and a centripetal force. I would stick to just the force and rotational modes, just straight up force and pressure modes for this project, just because I have a lot more experience with that. And I think in the past people have used rotational velocity, but I don't quite 100% understand it. And so, I would, I'm not going to stop you from using it. And so if you use it and you get results that kind of make sense to you, I would say just go for it. But haven't fully played around with it yet to really know how it really works. And so I would rather you just, if you do have a spinning part inside the bearing, you kind of compute the centripetal force kind of by hand and then just apply that as a normal force.
And we're gonna put Sally Mark in that chat. No, I think we're gonna do it. It might be better just to save them up for a week. And then that could be, but that's just my. No, well, the thing is, it's gonna looping lunges. Everything's weighted. That's the agreement. So the agreement is we start by pounds and every time the boxes. Yeah, so that's the thing is. Yes, that was my recommendation. And I was like, so, what you take on doing like lunges, like long lunges? It's like, you're not. I was like, so you want to stand still? Yeah. So he was like, what? And I'm like, yeah. This is what we're doing. So now it's me, him, and then one of our friends who's super. We're all part of this challenge. I'm excited. I'm super excited. I'm just kind of just doing it myself too. All right.
Hey, what's up?
Wait, so did you say gym will be approved for graduation?
Yes, and so that means that the courses that you're enrolled in this semester and the course you still have to take are a reasonable load. And so, that you still have to take those classes, but that means that you get a priority registration, you can participate in commencement. And so, but you still, you still have to complete all the courses that you still need to do.
Gotcha.
Are graduating.
Yeah, I did. No, I'm probably just. And so I just
This one, kind of how I thought about it was, because when we take the moment, we basically think as the force, we usually divide, so it's gonna be in the denominator.
Yeah.
So that's what I was explaining, but I think what kind of answer were you expecting?
Yeah, so for that one, we went over kind of the analogy in class where like,
Mhm.
you know, if you, when you have like a, you know, let's say an arm like this.
Yeah.
Right? And you have your muscle, the muscle kind of attaches kind of like this, right?
Yeah.
And so the moment arm is this distance right here.
Uh-huh.
And so what we found was that, you know, when you compute muscle force, it's generally, you know, some stuff, and it's
Yeah.
divided by the moment arm right here.
Right.
And so this is usually really small. So this is usually on the order of 3, 4, 5 centimeters. And so what we found was that the muscle forces are really big. And so what we said is that, you know, why don't we make this bigger? And so why wasn't the human designed so that, you know, we can, your muscles attach like over here, right? Because then LM here would be bigger. And
The
then
force is gonna be small.
exactly, but we don't see this. And so that's not, you know, humans aren't designed that way.
Yeah.
And so I was kind of asking, you know, why is this LM, why is it usually short as opposed to? And so the reason for that is that if you attach longer here, then if you wanted to rotate out like this
Yeah.
muscle would have to shorten a ton.
Uh-huh.
And so, you know, it would be less force, but it would be more distance it would have to cover. The muscle itself would be longer. And so with a smaller moment arm, yes, it requires more force, but then, you know, you can shorten just a little bit and then your arm. is right. That's what kind of meant right there. So when you have smaller moment arms, it makes, I mean, first of all, it makes your form factor a lot smaller. So you don't have muscles that kind of go all the way over. But then it also makes it that you can move at the cost of requirement. That's usually a trade-off. That's good in most cases.
Makes more sense. I think you might calculating it. So this is 5, 10, 13, and then 18.
Oh, okay, so that is a numerical mistake. So let me,
Yeah.
why don't you leave it with me? I'll put it over here and then I'll give you one extra point.
Okay, no worries.
Yeah, I'll bring this back up first.
Okay, yeah, no worries. Thank you.
Yeah.
And I was added just around the types of courses that kind of work. And I saw that there was a rotational one. Yeah. So I just want to make sure it worked the way that I put it as. So I have the blade facing this like really something like this. And then I added a rotational force here. So does that mean that it's gonna rotate like this entire point is gonna rotate like that, or is there gonna be a rotational force acting on this point?
It's going to be acting on that point. Twisting around. And so I've been telling people, I would just use regular. Actually, don't play. I would play around with these rotations. Honestly, I haven't done that much playing around. So I don't have understanding of what they're doing. I think those forces are kind of like more specific. But for this, I would just stick with this regular. Yeah, for that case, you can compute, you know, based on how fast you can compute based on like the drag coefficient, what the pressure will be. So we go ahead and erase this. Okay, all right, it's 5:30. Let's go ahead and get started. I got good evening, everyone. How's everyone doing today? Doing good, doing good. Everyone have a good weekend? Good. This is totally unrelated, but I've been telling people just because, you know, what are the odds of this happening? But my dad went to the Chargers game yesterday, and so this is the third game he's gone to at SoFi Stadium, and all 3 times that he's gone, the game is won into overtime. So it's kind of, but I texted him and said, wow, you're really getting your money's worth for entertainment there at SoFi. So yeah, money well spent. Yes, and at least this time they won.
What was that baseball game that went into like 18th inning?
That was Astros Mariners last week.
That's
That was
crazy.
2 games.
That's
And
two.
2 full games. You can see the crowd, like, no one's even in it anymore. They're just like, they feel forced to stay there, but
Yeah.
they were not.
And they got swept.
Yeah. Yeah, but yeah, kind of interesting things, what are the odds? What are the odds that it happens? It's like, he's enjoying himself, he's retired, so he's loving his things, but I'm not, because I have to work. That's why I was at the game. So all right, and so anyway, back to reality here. And so we're back to finite elements. And so what we're going to cover this week. So we have a full lecture week this week. So no ANSYS, we're not doing any more ANSYS until after the project due. Maybe not until spring break actually, or fall break. I'm sorry. And so we'll be in lecture for quite a while. But I know you guys are working on the projects. I know the activity is due I think tomorrow, and so I know you guys are working on that and the projects. And so I'm not worried about you guys having enough to do. You guys have plenty to do. And so so we're gonna keep busy. Right? And as we get closer, so I think we're about 2 weeks, a little bit less than 2 weeks out from the project due date. And so if you have any questions or you're having any issues with the project, definitely don't be afraid to reach out. And so you can come to my office hours and talk about it, or you can send me an email. I've had people message me on Discord. I've had a lot of things. So don't be afraid. And so I'm here to kind of help out. And what I generally see is that most people kind of run into a snag at least in one point in the project. And so, like I mentioned before, the sooner you start working on the project, kind of the sooner you can hit those snags and the sooner that I can help you out with those. And so, don't be afraid to reach out, and I'm here for you. Okay. All right. And so in terms of today's lecture, we're going to build off what we went over last week. And so last week we introduced this idea of the direct stiffness method. And so this is kind of a by hand way to solve finite element problems. And so we're going to extend that this week. And so, last week we just went over springs. Springs are probably the simplest element that you can think of. And so today we're going to extend that to a truss slash bar element. Okay? And what you'll see is that a truss and a bar behaves very similarly to a spring, but it's just the element stiffness matrix is a little bit different. But the exact same process that we went through last week in terms of how to solve these problems, we're going to do them again. It's just that the element stiffness matrix is going to be a bit different. Okay. All right, and so that's it for my announcements. And so, are there any questions I can answer before we get started for today? Okay, all right, so let's go ahead and get started. And so the topic for this week is truss equations. All right, and so truss elements, what I'm hoping is not something new to everyone. And so, probably you covered this back in statics way back when. So I know statics was a while ago. And so, what I'm going to show you here is kind of a finite element way to approach those problems and solve them to get, more or less the same results. But at the end of the day, we're still doing finite elements here. Okay, so before I kind of start talking about trusses, let me kind of remind you of the finite element problem solving process. All right, and so, we went over this at the beginning of class last time, but, it's always good to review it. And so the finite element process involves discretizing and labeling the geometry. Okay, so before you even go anywhere with the finite element process, you have to break up your geometry into elements, and you have to label all of the elements, with a letter or a number, as well as all the nodes. Okay, and so that's important. But for most of these problems, they're going to be done for you. Okay, step 2 to the process is the element stiffness matrices. Okay, and so after you've gone through and labeled, you've discretized and you've labeled all the elements, step 2 is to go to each of the elements and form their element stiffness matrix. Okay. Once you form the element stiffness matrix, step 3 is assembly. And so remember, in order to actually solve a finite element problem, we have to have one single large linear system, okay? And so that's assembly. And so that's taking all the little tiny linear systems and combining it into one big one. Step 4 is boundary conditions. And so remember, when we apply boundary conditions in this kind of manual format, then we're modifying our global linear system, okay? And we do this in order to make it into a solvable system, because if we don't do it, there's literally no way we can solve it. Okay, and then finally, step 5 is we solve. And so, step 5 is actually the easiest part of this entire journey because you don't actually do it yourself. And so, all you have to do is basically set up the problem. You get the global stiffness matrix, you get the global forcing vector, you feed them into MATLAB, and you let MATLAB do all the hard work for you. And then MATLAB is going to give you an answer for all the nodal solutions. Okay. Okay, and so, even though we're talking about trusses here, we're still going to be following the same process. The only difference is that in step 2, we're going to be forming the element stiffness matrix for a truss instead of a string. Okay. So that's kind of the big difference. And that's kind of the big difference between most finite element methodologies is how you form the element stiffness matrix based on the type of elements that are available. Okay. Okay, and so let's go ahead and introduce trusses. And so a truss is a slender structural element that we assume can only be compressed or stretched. And so visually, we kind of represent it as just kind of a thin tube, just like this. Okay. So this tube here of length L. Okay. We also know the material for this truss element, and so we also know its Young's modulus. E. Okay. And then one thing we'll also know is the cross-sectional area where the cross-sectional area is A. Okay. So those are the 3 main properties for the truss that we're going to be working with. Okay. And our assumption here has to do with its modes of deformation. Okay. And so we're only going to assume that it can be compressed and stretched. That means the deformation is going to be purely in the axial direction of the truss. Okay. Okay. And so when we're characterizing the deformation D1, D2, we're going to only assume that it's going to be, down the length of the element. Okay, it's either going to be, stretching it out or compressing. I'll go ahead and label these nodes. And so the node on the left, I'll call node 1, and the node on the right, I'll call node 2. In addition to the deformation, we also have the forces that are on each node. Okay, so we'll call that F1, F2. Okay. So I'm gonna go ahead and write that down. Okay. We have D1, D2, F1, F2. I drew T in there. I was a little bit premature with that. And so, we're going to use T in a second. But basically, what we want is we want to have a relationship between D1, D2, and F1, F2. And that relationship is going to be our element stiffness matrix. Okay. Okay. And so that's basically what we're going to seek to obtain. So, this first part of the class here is, we're going to obtain the element stiffness matrix for this truss, and then we're going to use that element stiffness matrix in problems. Okay? And that's kind of the general trend of what we're going to be following over the next couple of weeks. And so, I'm going to be over the next couple of weeks, I'm going to be introducing to you different types of elements. And then from those elements, we're going to form its element stiffness matrix. Okay, we're going to derive it in some way. And then from the element stiffness matrix, we can then use that to do problems and such and such. Okay. So this truss element here will be the second type of element that will go over this direct stiffness section. Okay, any questions on this so far? All right, and so, just in the way that I've drawn it here, you should see a lot of similarities with the spring. Okay, and so very similar to a spring, if you think about a way that a spring is expected to deform, a spring deforms in exactly the same way. And so a spring can only compress and it can only be stretched. Okay, and so we say that the deformation for a spring is only in the axial direction. And so that's exactly the same here that we have with the truss. And so what you should generally expect, kind of as we go through this derivation here, is that the element stiffness matrix for this truss should look very similar to our spring, except, we don't have a spring constant, but, instead what we have are these quantities, but you'll see it all kind of make sense. Okay. And so just like we did with the spring, we're going to assume that this truss element is in static equilibrium. Okay. And so we're going to assume that we have an equal force of T, a tensile force of T applied on both sides of the truss. Okay? And we're going to use that to form our relationship between, F1, D1, and F2 and D2. Okay. So another thing we're going to assume is that we're going to assume we have linear elasticity inside the bar. And so what we know from linear elasticity is that the stress is linearly related to the strain. Okay. And so we have Hooke's law. So we have stress. Here, of course, is our Young's modulus. And epsilon here is our strain. Okay. So this equation here, this is going to form kind of the basis for our derivation and our element stiffness matrix. Because what we're going to do here is we're going to substitute for each of the terms here, except for E. And then what you see, we can put them in terms of the quantities that we know. Okay. Okay. Okay, so let's start with sigma. And so we know that sigma is a stress, where stress is nothing more than just a force distributed over an area. And so what we can say is sigma here. And so we know the force that's acting on this bar. And so we know that we have a tensile force T, and we're also given the cross-sectional area. And so we can substitute for sigma as T divided by A. Okay. Next, we have the strain. So we know that the strain here represents a relative change in length. So strain here, which is epsilon, is equal to dd dx. Okay, so we're the second D there is deformation. And so it's the change in deformation over x. Okay. And so of course we can use kind of a finite difference representation for this derivative. And so we can represent this as the nodal deformations. So we have d2 minus d1. Okay, divided by the original length, which is L. Okay, so we say strain is equal to d2 minus d1 divided by the length. Okay. All right, so let's go ahead and plug these in. Okay. And so on the left-hand side, we have sigma, which is T over A. This is equal to E, the Young's modulus, multiplied by our strains. This is D2 minus D1 divided by L. Okay. Okay, so all I did was I plugged in our expression for sigma and epsilon into our equation there. And so I'm going to go ahead and simplify this. So I'm going to go ahead and solve this for T. Okay, so I'm going to isolate T on the left-hand side. And so we're going to have, I'm going to multiply both sides by A. So we have T is equal to A times E divided by L times D2 minus D1. Okay. So now that we have an expression for T, you know, we know that T here is being applied on both ends of the truss. Okay. And so let's go ahead and mathematically relate T to F1 and F2. Okay. All right, so let's go back up to our figure here. And so if we go back up to our figure here, we can see that T is being applied to the left-hand side of F1. Okay, so T is going to the left on node 1, whereas T is going to the right on node 2. Okay. And so what we can do is you can say that F1 here is going to be equal to negative T, right? Because the force that's being applied on node 1 is, T, but has a magnitude of T, but it's going to the left. Okay. Whereas the force that's being applied on node 2 is going to be exactly T. Okay, so F2 there is going to be equal to T. So let's go ahead and plug in our expressions for this. So we can say that F1 is equal to minus AE over L times D2 minus D1. And F2 is equal to positive AE over L times D2 minus D1. Okay. Just for simplicity, I'm going to go ahead and distribute the negative for F1. And so we have AE over L times D1 minus D2. Okay. For F2, there's nothing really to, there's nothing really to distribute. So I'm going to leave it as it is. And so now that we have this expressions here, we can see here that we have equations that have F1, F2, D1, and D2. Okay. So let's go ahead and use these two equations to form our stiffness system. Okay, so I'm going to say F1 is equal to AE over L times D1 minus D2, and F2 is equal to AE over L times D2 minus D1. Okay. Now me go ahead and put this in matrix form. Okay. Because what we have is a system of two linear equations and two unknowns. Okay. And so of course we can put this in matrix form. And so we have F1, F2 is equal to matrix AE over L minus AE over L minus AE over L, AE divided by L times D1, D2. Okay. We can factor out just to kind of save our fingers a little bit instead of having to write AE over L so many times. Because it's a constant multiplier, we can pull that out of the matrix. So we can say this is equal to AE over L times 1 minus 1 minus 1, 1, F1, F2, D1, D2. And there is our stiffness system. Or this right here, that right there is our element stiffness matrix for a truss. All right, and so that's it. Okay, and so there's our element stiffness matrix for a truss. And so now that we have that, we can go ahead and just start solving problems with this. Because we've already gone over the entire direct stiffness system. The only thing that was unknown to us up to this point was how to form the element stiffness matrix for a truss. But now that we have that, we're ready to start doing some problems. Okay? So the next thing I'm going to do is an example. But before I do that, are there any questions on this? Okay. All right, so let's do an example. So in this example, we're going to have an assembly of 3 truss bars. So we're going to say the truss bars are kind of, they're sandwiched between two fixed walls. Okay. So here we have element A, element B, element C. Okay. We're going to assume that the total length of the entire assembly here is 90 inches. But the length for each element individually is 30 inches. Okay. And so we're going to assume that they all have the same length. Okay. And so in addition, we also have information on the Young's modulus. Okay. And so we'll assume that elements A and B are made of a certain material where the Young's modulus is 30 times 10 to the 6 psi. Whereas element C has a Young's modulus that's half of that. And so the E for element C is 15 times 10 to the 6 psi. All right, we also know the cross-sectional area. So for elements A and B, they have a cross-sectional area of 1 inch square. Meanwhile, element C has a cross-sectional area of 4 inch square. Okay. So even though element C here has half the Young's modulus, the cross-sectional area there is quadruple. Okay, so we have 4 times the area. All right. So let me go ahead and label the nodes here. So we have nodes 1, 2, 3, and 4. And so, oh, we need to force 2. And so let's assume that we have somebody grabbing onto the middle of this assembly. Okay. And so let's assume that we have a force here, and the force is equal to 3,000 pounds. Before I forget, it may be clear from the figure, but let me just go ahead and label it just to be sure. And so because nodes 1 and 4 here, they're kind of attached to the lateral walls, we're going to assume that nodes 1 and 4 here are fixed. Okay. And so given this problem here, and given its all of its features, what we're going to compute, or what we want to compute, are the nodal forces at, or excuse me, we're going to compute the nodal displacements at each of the 4 nodes. Okay. And one new thing that I'm going to show you how to compute in this problem too is we're going to compute the reaction forces at the 2 fixed supports. All right, so we haven't gone over how to do part 2 of this problem, but we'll go over that once we get there. We need the nodal displacements first before we can actually do that. All right. Any questions on the setup for the problem? Quite a few things going on here. So a lot of numbers and a lot of diagrams to see. Okay, so if there's no questions, let's go ahead and get started with the solution. And so, we're going to be using the direct stiffness method to solve this. And so we're going to be following this exact same recipe that we went over at the beginning. Okay. And so we've already discretized the system, and so we've already labeled everything. And so the next step is to do the element stiffness matrices for each of the elements. Okay. And so we have 3 elements here. And so that means we're going to have 3 element stiffness matrices. Okay. And so we know for a truss, the element stiffness matrix is AE divided by L times 1 minus 1 minus 1 and 1. Okay. So for element A, if we go ahead and compute that, so we have AE over L. AE over L here is going to be 1 inch square, which is the area. E here is 30 times 10 to the 6 psi. And the length here is 30 inch. Okay. So if we do the math here, we know the 30 here is going to cancel out. We know that the AE over L factor for element A is going to be 10 raised to the 6th power. Okay. So let's go ahead and plug that in. And remember, when you're forming the element stiffness matrices for the elements, you have to note on which node the elements are attached to. And so in this case, the element A here is attached to nodes 1 and 2. And so this is going to be F1, F2. It's going to be multiplied by 10 to the 6th. 1 minus 1 minus 1 1. Okay. And then we multiply it by the nodal displacements D1 and D2. Okay. And so our total element stiffness system for element A is going to be F1, F2 equal to 10 to the 6th times 1 minus 1 minus 1, 1. And that's multiplied by D1, D2. Question? Yeah. Yeah, great question. And so the units for this, so PSI here is pounds per square inch. Okay. And so the inch square is going to cancel out. And so the units for this is pound per inch. Yeah, so that's generally the units for the stiffness matrix. So it's going to be some force divided by a distance. Mm-hmm. So same units as a spring constant. Okay, so that's element A. So let's go ahead and repeat the process for element B. Okay, so element B has identical AE over L, and so I'm not going to write the formula for it again. And so for element B, we know that the AE over L is going to be 10 to the 6th pound per inch. So let's go ahead and write out the element stiffness matrix for it. But remember, element B here is attached to different nodes. And so element B here is attached to nodes 2 and 3. And so we have to make sure that we account for that. So we have F2, F3, so 10 to the 6th, 1 minus 1 minus 1, 1, D2 and D3. Okay. And then finally, we're going to repeat this for element C. And so for element C, we're going to do AE over L. So the cross-sectional area for element C is 4 inch square. The Young's modulus is, again, 30 times, so element C has a different Young's modulus, so it's only 15. 15 times 10 to the 6th psi. And then the length is 30 inches. Okay. All right, and so if we work out the math for this, and so we have 15 divided by 30, and so 15 divided by 30 is 1/2. And if we take 1/2 times 4, then that's going to be 2 times 10 to the 6th pound per inch. Okay. So our element stiffness matrix for element C, noting that element C here is attached to nodes 3 and 4. And so this is going to be an F3, F4 equal to 2 times 10 to the 6th times 1, minus 1, minus 1, 1, and then D3, D4. So that's the, those are the 3 element stiffness matrices. Okay, so we're done with that step. And so the next one is going to be assembly. All right, any questions on this? All right, so next we're going to assemble this. So remember, for assembly, we're going to put this into one gigantic system. And so let me go ahead and put all the nodal forces here. Okay, so F1 through F4. Okay. And we're going to have D3 through D4. Okay. And then let me go ahead and label the columns here too. So D1, D2, D3, and D4. All right, so now we need to insert the 3 elements into here. So let me go ahead and label them as colors. Okay, so first we have element A. Element A we know is nodes 1 and 2. Okay. Okay, so you can go ahead and box in the area where element A is going to be taking place. Okay. And so that's the nodes D1 and D2. Okay. And so we fill in the entries in element stiffness matrix for A. We have 10 to the 6, minus 10 to the 6, minus 10 to the 6, 10 to the 6. Okay. Okay, then we have element B. Element B is nodes 2 and 3. So let me go ahead and box those off. Okay. And so that's element B. And so element B has entries of 10 to the 6th, minus 10 to the 6th, minus 10 to the 6th, 10 to the 6th. Okay. And of course, whenever we see overlap, we're going to just add those entries together. And so in that overlap spot, we have 10 to the 6th plus 10 to the 6th. And so that's going to be 2 times 10 to the 6th. Okay, and then finally, we have element C. Element C is nodes 3 and 4. Let's go ahead and box that off. Okay. And the entries for this are 2 times 10 to the 6th. And so let's go ahead and add all those in. Okay. We have a 2 times 10 to the 6th, minus 2 times 10 to the 6th, minus 2 times 10 to the 6th, and then 2 times 10 to the 6th. Okay. Once again, we have an overlap. So let's go ahead and add those entries. And so if we add those there, we get 3 times 10 to the 6th. All right. So that's the assembly of that problem. And remember, anything that's not boxed, we can just put a 0 there. Okay. All right. Any questions on this so far? All right, and so we're in a good spot here. And so the next step after assembly is boundary conditions. Right, so remember boundary conditions, we're gonna modify our assembled system in order to make it solvable. Because if you try to plug in that system right now into MATLAB, first of all, you don't have any values for F1 through F4, and so you can't solve it yet. Okay. Okay. So just for simplicity, I'm going to go ahead and write the system out again. So we have F1, F2, F3, F4. D1, D2, D3, D4. And then the entries in the matrix, we have 10 to the 6th, minus 10 to the 6th, minus 10 to the 6th, 2 times 10 to the 6th, minus 10 to the 6th, minus 10 to the 6th, 3 times 10 to the 6th, minus 2 times 10 to the 6th, minus 2 times 10 to the 6th, and 2 times 10 to the 6th. Okay. Everything else is zeros, but we're going to overwrite some of this anyway, and so I'm just going to leave them blank for now. Okay. And so we have 3 boundary conditions that we need to apply here. And so we have 2 fixed constraints. Okay. And so those are fixed constraints on nodes 1 and 4. And so we're going to apply those. We'll probably do those ones first. Okay, and then we also have a load of 3,000 pounds, which is being applied on node 2. Okay. All right, so let's start with the constraints. And so remember, the way that we deal with constraints is that we go to the rows on which the constraint is being applied, and we replace those entire rows. Okay. So we're going to replace row 1 and row 4. Okay. Okay, and those are going to be our fixed constraints. All right, and so if you recall, the way that we do this is that we set the F values, or we set the forcing values in those rows equal to 0. Okay. We put a 1 on the diagonal entry. Okay, and so whatever the diagonal is for that row, we're going to put a 1 there. And so for the first row, the diagonal entry is the first column, and for the 4th row, the diagonal entry is the 4th column. And then everything else on that row is going to be zeros. Okay, so we have 1, 0, 0, 0 for the first row and 0, 0, 0, 1 for the last row. Okay. And then the last thing that we need to do before we can solve this is replace F2, F3 with their appropriate load values. And so if we look back on the problem, F2, or the force that's being applied on node 2 is 3,000 pounds. Okay. And so we're going to erase F2 here, and we're going to replace it with 3,000. And then we're going to release or erase F3, and then replace F3 with 0. Because there's no force being applied on node 3. So let me go ahead and fill in the rest of the zeros. And so we have a 0 here, a 0 here. Okay. Now this system here is ready for MATLAB because we've assembled our system, we applied the boundary conditions, and now we're ready to solve this in MATLAB. So before we do that, are there any questions on how we apply the boundary conditions here? Yeah. Yeah, so remember the diagonal entry is just whichever column is matching that row number. And so for constraints, we put a 1 on that entry. Yeah. So whichever column matches that row number. So for row 1, that's going to be column 1, and for row 4, it's going to be column 4. Okay. All right, and so now that we have the system the way it is, let's go ahead and plug it into MATLAB. And so I'm going to skip that step just because I don't want to switch to my computer here. But remember the way that we put this into MATLAB is that we define 2 variables. The first variable is going to be our stiffness matrix. Okay, and so it's going to be a 4x4 matrix where the entries in the matrix are given by the following. And the second variable that we're going to define in MATLAB is the forcing vector, which is all of these. Okay. And so if we do that, we use the magical backslash, then what we get is the following. So we get D1 is equal to 0 inches. Okay. We get D2 is 0.0018 inches. D3 here is 0.0006 inches. And D4 here is 0 inches. Right. So that's our solution. So we've gone through the whole process again of the direct stiffness method, except now we've done it with trusses. And so not much has really changed. And so the only thing that really changed is that instead of our element stiffness matrix being comprised of spring constants, instead we have the truss parameters, which are the area, the Young's modulus, and the length of the element. All right, any questions on this example here? Okay. All right, and so that's a part 1 of the problem. Part 2, remember, is to solve for the reaction forces that are holding this structure up. Okay. And so in terms of reaction forces, what this means is that in order for this structure to be in static equilibrium, there must be forces applied at the fixed constraints to make sure that the net force on the structure is 0. Okay. Okay. Right, because the only finite element situations that at least that we've seen so far all involve just static situations. And so whenever you have a force like we have here of 3,000 pounds being applied on a structure, there must be equal and opposite forces being applied by the constraints to make sure that, you know, the structure doesn't go, with rigid deformation. Okay. Okay, and so what this means basically is that everywhere that we have a fixed support, there has to also be a reaction force at those places. Okay. And so for this particular problem, our fixed supports are located on nodes 1 and 4, excuse me. And so we should solve for F1 and F4 that'll keep this structure in static equilibrium. Okay. And so to do this, you know, it's actually simpler than you think. And so, you know, we don't have to do any free body diagrams or anything like that. What we can actually do is we can utilize the solution that we already have and a global stiffness matrix that we've already computed. Okay. And so all you have to do is we're going to multiply two things together. So one of them is a matrix and the other is a vector. And so the first thing you're going to multiply is the solution vector that you just solved for. And so the values for D1, D2, D3, and D4. Okay. So we just solved for those. And the other thing you're going to multiply is the global stiffness matrix from the assembly step, okay? And so this is pretty crucial. And so this is going to be before we apply the boundary conditions. Okay. And so if you remember, you know, when we're going through our direct stiffness process, you know, we actually had a global stiffness system where after we assembled all the element stiffness matrices, and then after that, we modified that system according to the boundary conditions. And so what you're going to want is actually that global stiffness matrix before you apply the boundary conditions, and you're going to multiply those two things. Okay. All right, and so for this problem, we're going to perform this multiplication here. And so let me go ahead and write down the global stiffness system before we applied boundary conditions. So that was 10 to the 6th minus 10 to the 6th, 0, 0, minus 10 to the 6th, 2 times 10 to the 6th, 10 to the 6th, 0, 0, minus 10 to the 6th, 3 times 10 to the 6th, 2 times 10 to the 6th, minus 2, 0, 0, minus 2 times 10 to the 6th, 2 times 10 to the 6th. Okay. And so if you look back into your notes, you know, this is the global stiffness system we had before we applied boundary conditions. Okay. Notice that it's symmetric, so you should get a symmetric system here. And then what we're going to do is we're going to multiply this by our solution. And so if we look back up here, our solution is the following. And so we had 0. For D2, we had 0.0018. For D3 here, we had 0.0006. And D4 is 0. Okay. All right, and so why are we doing this? And so, you know, if you go back to our stiffness system before we apply the boundary conditions, you can see that these things are exactly F1, F2, F3, and F4, okay? And so since we've already solved for D1 through D4, you know, all we have to do is just go back to that system there. And so this can give us F1, F2, F3, and F4. Okay. And so all we have to do here is just perform the matrix vector multiplication. Okay. And so of course you're welcome to do this by hand. It's not as bad as solving a system of linear equations, but it can still be quite tedious. And so if you know how to multiply matrices and vectors in MATLAB, that's going to help you out tremendously here. Okay. And so if you do that, then what we get is F1. F1 here is minus 1,800 pounds. F2 is still 3,000 pounds. F3 is 0 pounds. And F4 here is minus 1,200 pounds. Okay. And so if you want to check your answer here, you can make sure that if you sum up all the forces that they equal to 0. Okay. And so we take a minus 1,800 plus 3,000 minus 1,200, then that equals 0, which is good. Okay. Another way you can check your answer is that you actually get forces at places where you have the fixed constraints. And so remember, we had the fixed constraints on nodes 1 and 4. And so you can see we have forces there now. Okay. The applied loads are still the same. So we still have our applied load of 3,000. And then F3 here is still 0 because we neither have a load nor a constraint on that node. And so there should be no force applied there at all. Okay. All right, any questions on this? All right, so finding reaction forces is pretty straightforward. You just have to take your solution and just kind of plug it back in elsewhere. Okay. All right, and so for truss problems in 1D, there's really not much more to that, and so that's the only example that I have, just because it's basically the same as springs. But now that we're done with 1D, we're ready to move on to the second dimension, which is 2D. Okay. And so let's go over how to do truss and spring problems in 2D. Okay, so you might be wondering, why are we bothering to go to 2D? Okay. Well, it would be very simple and very great if our entire world consists of just 1D stuff. It would be a lot more boring, but it would be a lot simpler. But unfortunately, we don't live in that world. We live in a three-dimensional world. And so to do, more complicated problems, of course, you're going to have to go up in dimension. And what you'll see is that, going up in dimension actually adds a fair bit of complexity to the problem. And so I don't know if they do that here. I haven't sat in on like a physics class or anything. But I remember when I was in college, and they would teach us stuff in like mechanics or electromagnetism or whatever, they teach us the 1D theory. And then the professor will kind of wave their hand and be like, oh, you can extend this to 2D and 3D. It's easy. It's just the same thing. I don't know if they do that here, but I know that was always the case. But I know for sure that when you go from 1D to 2D, it is not the same thing, and it's very different, and it's a lot more hard. And I think we should respect that fact. And so so the same is going to go here for finite elements too. And so when we go from 1D to 2D, there is a lot of complications and a lot of extra work that we have to do. And I think it's important for you guys to see that because underneath the hood, when you're doing ANSYS and stuff like that, ANSYS is doing a lot of these things. And so it's good to know what ANSYS has to do in 2D and 3D. And so, I don't leave you with kind of a false impression that, finite elements is easy. And so, it's something like that. Okay? There is a lot of complication that goes into multi-dimensions. We're not going to go to 3D just because at that point, it just becomes majorly tedious without really much benefit. But I think going from 1D to 2D, I think gives you a good look at, what you need to do to extend FEA to multiple dimensions. Okay. And so this is a discussion that we'll probably start it today, and then, and we'll pick up the details on Thursday. Okay. But I first want to start off by introducing different coordinate systems. Because the way that we're going to apply things in 2D is that, we are going to have to rotate our coordinate systems quite a bit. Okay. And by coordinate systems can mean quite a few things. And so in this case, what I mean by coordinate systems are the orientations of the X and Y axes for our spatial measurement. All right. And so the first coordinate system that I'm going to introduce is what's called a stationary coordinate system. Okay. And so our stationary coordinate systems, you can think of this as like our standard X and Y. And so the stationary X direction is going to be just horizontally from the left to the right. And the stationary Y direction is going to be perfectly vertical from, bottom to top. Okay. And so these are often called, I call them the stationary coordinate system because it doesn't move. And what they're going to do is they're going to serve as our point of reference for all the other coordinate systems. Okay. All right. And so besides the stationary coordinate system, we can also have what's called local coordinate systems. And so local coordinate systems are oriented to be parallel to a specific element. Okay. Okay. And so for instance, let's say we have a 2D situation where we have a truss element that's kind of going up vertically or going up, from the bottom left to the top right. Okay. And so we might have a system like this, okay, where we have an element that's kind of oriented like this. And so what we can do is that we can orient our coordinate system to be in line with that element. Okay. All right, and the way that we're going to track the rotations here is through that angle theta, which you may have already written down on your sheet. Okay. And so that angle, very important, that angle is going to be measured relative to the stationary x-axis. Okay, so it's the angle between the stationary x-axis and the local x-axis. Okay. Conversely, this is also going to be the angle between the stationary y-axis and the local y-axis as well. And so one thing you can draw here is you can draw a vertical line, and this angle is also going to be theta. Okay. And so we're talking just pure rotations here. And so, we're not going to do any kind of coordinate axes translations. And so we're just rotating the local axis relative to the stationary. Okay. And the defining characteristic, will be that angle theta. All right, and so our goal here, and so what we want to do is we want to form a relationship between these two systems, okay? Because even though we have different systems right here, they still both exist. And so what we can do is, we can use both systems and define the same vector. We can define the same vectors in one system. We can define that same vector in the other system as well. Okay. And so what we want is kind of a mathematical relationship that maps between the two coordinate systems. Okay. Because if I were to take these two systems and if I were to draw a vector here, okay, so if I were to draw a vector u, and if I were to draw that same vector u, and let me try to draw it as identical as possible. Okay. And so if I were to draw the same vector u in both coordinate systems, it could be the exact same vector. But how we describe it in terms of its components is going to be different depending on the coordinate system. Okay, so so we can describe this vector in the stationary coordinate system. We can describe it in the local coordinate system. Okay, it's going to have different components because the coordinate systems are different, but it's still the same vector. Okay, and so it all just really depends on your perspective. Okay, so this is another way to see this is. We're looking at different perspectives. We're looking at the same things in different perspectives. Okay. Right, and so one way that we can say this, we can say that we have ux and uy. Okay. This may be the components of u and the stationary coordinates. And then we also might have, what do I use? I use primes. And so I'll have ux prime and uy prime. Okay. These are going to be the coordinates of the same or components of the same u in and so if this u is exactly the same, and so it's the same u vector in both cases, then these two should be equal. And so if we were to put this in vector form, then we would say this is ux times I plus uy times j is equal to ux prime I prime plus uy prime j prime. So obviously, ux, uy, ux prime, uy prime, those are going to be different from each other. Okay. And the thing that makes this equal is the fact that I is different than I prime, j is different than j prime. Okay. So I and j here These are unit vectors in the stationary X and Y directions. Meanwhile, I prime and J prime, these are unit vectors in the local X and local Y directions. So in order for this relationship to work, in order for this equality to hold true, there has to be a relationship between I and J and I prime and J prime. Okay? And so what we're going to do on Thursday, just because we're just about out of time today, what we're going to do on Thursday is we're going to form that mathematical relationship. You'll see that it's fairly simple. It's just just some trigonometry, and then we'll see how this is and how we can use that information to transform our element stiffness matrix for our truss and for our springs too. Okay. All right. Any final questions on this before we wrap it up for today? Okay. All right. So that's all I got for you guys today. And so thank you guys for tuning in or for coming out. So we hope you guys enjoy the rest of your evening, and I will see you guys on Thursday. All right, is there a good time I'm available to answer some questions about problem 7 on activity 4? Yeah, I'm free right now. If you want to, how long do you think it's going to take? Yeah, I can answer right now. You want to do you want to share your screen? Okay, let me go ahead and stop here. Okay. So you're free to share, Jaden. Problem 7, if I recall, that's the one where you do with solid elements, right? Yeah. So for that one, that one's just like a try and see. And so I will say that personally, I've never been able to do that one. And so I always get an error with that whenever I try with solid elements. I think I was able to do it once maybe, but there have been some students that are able to do it. I think it depends on if your computer is liking you at the moment. So if you're running into an error for a problem 7, then just say you're running into an error, and that's generally the expected result. Yeah. So I chose this geometry. Okay. Oh, okay. I see. Oh, I see. Yeah, if you want to do it with solid elements, you do have to start over. And so I would just create a separate project for it. Just upload the geometry again, and then just try meshing it. Yeah, you can try, but don't stress too much about it. Yeah, don't. If you're getting an error, then just that's what I get too. And so that's the expected result. Yeah, if you're getting an error during the meshing, that's what I get too. And so if you're getting an error, then yeah, don't worry about it. That's what you should get. Yep. Okay. All right, Charles. Any final questions? Oh, for sure, yeah. And I think if you had a better license, then you could probably do it, but it's very difficult with the student license. Okay, I'm gonna close it up. So I'll see you guys Thursday.